Good morning, ladies and gentlemen. Welcome to today's video. Today, we're going to talk about the conditions for the sampling distribution of sample means and basically what each condition does for us with regards to how the X bars will be distributed. But before we get into that, you might notice that the logo is missing. So some developments, the two students that developed the logo sort of pushed back and were demanding some sort of royalties for the use of their logo. And I refused. And so I took it down. I did go ahead and create my own logo. So this is the world premiere of the new Couch Potato Brand Snack Food and Beverages logo. All right, there it is. And very minimalistic. I've honestly never been prouder of anything in my entire life. So I hope you like it. And with that being said, let's get on to today's video. I'm your host, Mr. Giratina. I don't know how this is actually pronounced, but people think it sounds like my name. All right, so back to the actual topic. We're talking again about the conditions for the sampling distribution of sample means. All right. So let's just imagine that we have some sort of quantitative variable. Quantitative meaning some sort of numerical value that has units of measure, right? So for example, let's define X to be ounces of Couch Potato Brand snack food and beverages eaten per day. So the parent population, let's say like the entire Bronx science community, that's our parent population. That entire community has some average amount of ounces per day, and there's some standard deviation of ounces per day. The shape, not sure what it is. It doesn't matter though. But just to give you a sense of what I mean, the shape could be something called uniform. So actually that shouldn't be X. This is X. So let's say X goes from, so the number of ounces eaten per day goes from 0 to 400. I know it might be even more than that, but let's just say we cap it at 400. Maybe for each value between 0 and 400, there's the same number of people or the same proportion of people eating that number of ounces. Or maybe the distribution of number of ounces eaten looks kind of like this. There are a lot of people that eat very few ounces of Couch Potato Brand snack food. And there are a few people that eat a lot of Couch Potato Brand snack food in ounces. Again, this should not be X. All right. Or maybe there's a normal distribution or a symmetric, let's say, distribution of people that eat Couch Potato Brand snack food. Few eat very little, few eat a lot, but a lot of people eat a decent amount, a middle amount. Or who knows, maybe the shape of the parent population is something crazy like this, where there's a bunch of haters here, but then there's a whole bunch of fans, people that eat a lot. Who knows? Point is, it doesn't matter, because if we wanted to study Xbar, which is the average ounces eaten in a sample of N people from this population, it turns out that there's a very predictable pattern of how X bar, how your sample means will be distributed. And what I mean by how your sample means will be distributed, assuming we went into the population and took a whole bunch of little samples and got a whole bunch of X bars. Here's X bar 1, X bar 2, X bar 3, X bar 4, and let's say here's X bar infinity. In theory, let's say we went out and we chose every possible combination of N people that we can from this population. Of course, these X bars, they're not all going to be exactly the same. Why? Because each sample is going to contain different people, right? So some X bars are going to be higher, some X bars are going to be lower. The amazing thing is, though, as long as certain conditions are met, we know exactly what the shape of the distribution and what the center and what the spread of the distribution of X bars will be. And so how will X bars be distributed? At this point, we're not sure, but if the central limit theorem, if the conditions for the central limit theorem are met, then we will know. So let me remind you, the central limit theorem, to put it very simply, says that if certain conditions are met, then our sample means will be distributed normally. They will be centered at the parent population's mean, and the standard deviation, or the standard error, as we use in the context of sampling distributions, so the spread of the sampling distribution of means, will be equal to the parent population standard deviation divided by radical n, where n is the sample size of each of these little samples that we went ahead and selected. All right. So if conditions are met, we know for sure this is exactly what our X bar distribution will look like. And that's important because it allows us to run certain inference procedures like hypothesis tests or confidence intervals to study to study means, to study certain populations and make claims about populations. As you well know, we've done plenty of hypothesis tests and confidence intervals. So anyway, the point of the video, what are the conditions? And what exactly does each condition do for us? First off, we have this thing called the nearly normal condition. Okay, first of all, this can be checked in two ways. So the nearly normal condition, you might ask yourself, is n greater than 30? If that is the case, then the nearly normal condition is met. You don't have to do anything further. If not, though, then you might ask yourself, is the sample, so the group of people that you went in and pulled out of the population and then calculated an average for, that sample, is that sample of ounces eaten nearly normal? Right, because to get each one of these X bars, there are going to be a certain number of people. Let's expand this first sample a little bit larger. And inside of this first sample, there are, let's say, 10 people. And the first person eats 2 ounces per day. The second person eats 5 ounces per day. Back to 2, 3, 8, 10, 3 again, 11, 12, and 7. Okay, so this is a small sample size. It's only 10. So the nearly normal condition isn't met by n being greater than 30, but what you would do instead to check is you take these points, you plug them into your maybe list 1, and you check the normal probability plot. Is the normal probability plot approximately linear? If so, then this sample would be said to be nearly normal. I don't know off the top of my head if this sample is nearly normal. I don't really think it is, to be honest, but anyway, that's not the point. So that's how you would check if n is not greater than 30. Is the sample itself nearly normal? Okay. Now, if the nearly normal condition is successfully checked off, what does this do for us? Well, this ensures that this is what ensures the shape of our Xbar distribution. Specifically, it ensures a normal distribution of Xbars, which is an incredible result, and it's one that is extremely useful. Again, like I said, when we're doing inference procedures. So the nearly normal condition is the condition that guarantees us the normal shape. There we go. Shape is satisfied. Then there's the random representative sample. This is it's identical to what we discussed yesterday with proportions, except what this does is upon repeated sampling, we would obtain an unbiased estimate of the population parameter. In this case, the parameter of interest is mu. So what this does is it tells us that our normal distribution of X bars will be centered. In other words, its mean will be mu. So that random representative sample condition gives us the center of the distribution of X bars. And then again, the 10% condition, once again, very similar to yesterday. The 10% condition, it helps us obtain independent samples. And again, upon repeated sampling, so if we obtain many X bars with the same sample size, there will be a specific and guaranteed spread. And when I say the word spread here, I'm referring to standard deviation, which in the context of a sampling distribution, we say standard error. But that spread will be, like we mentioned earlier, it will be the parent population standard deviation divided by radical n. So we have our three conditions. One gives you shape, one gives you center, one gives you spread. And there we have it. Now, one other sort of complication that we discussed already when referring to analyzing sample means is if we're running an inference procedure, and when I say inference procedure, I'm referring to either determining a confidence interval to approximate mu, or we're running a hypothesis test on some assumption about mu. Then in that situation, both the population mean and the population standard deviation are unknown. Yesterday, when we were talking about the distribution of p hats, notice that there's really only one parameter that we're interested in and only one parameter that's unknown, and that is this value p. P is the only thing that unknown. Well, you might say, oh, Q is unknown also. Yes, well, Q is just 1 minus P. So if you look at the parameters of the sampling distribution of P hat, there's really only one unknown piece of information. And really, so there's only one thing that we're kind of approximating or inferring about. However, that's not the case with means when we're running hypothesis tests or confidence intervals on means. Both mu and sigma are unknown, and they obviously play both, well, way too far. They both play prominent roles in the sampling distribution, all right? So the fact that both of these parameters are unknown, this leads to additional uncertainty. And that additional uncertainty is what led someone named William S. Gossett to develop what's called the t-distribution. Now, I went into this in detail in my other video about a month and a half back now. So if you want the details, please go check that out. This is just meant to be sort of an overall review video. So anyway, William S. Gossett developed what's called the t-distribution. And so anytime we're running an inference procedure and and we have an unknown mean and an unknown standard deviation, we use what's called the t-distribution to analyze this situation. And it turns out that the t-distribution is just like the normal model, it just has larger tails. Those larger tails are what we mean when we say that we are accounting for the uncertainty. Okay. So the t-distribution is same parameters centered at mu with a spread of sigma over radical n. Of course, in an inference procedure, we don't know our spread. And so what we do is we typically use the sample standard deviation in order to approximate it. So you'll typically find this value as S over radical n, but just please understand that that is an approximation. Okay, ladies and gentlemen, I believe I have said all that I have needed to say. So please, if you have any questions about any of this, feel free to ask me. Again, refer back to the t-distribution video if you want more specific details about why the t-distribution, so on and so forth. All right, hope you enjoyed the video. Take care.